Although carburetors haven't been used on vehicles sold in the United States since the 90s, there's still millions and millions of vehicles on the road that use them. If you're into vintage cars, hot rods, muscle cars, anything of an era before fuel injection, and you own one of those cars, you need to know a little bit about how a carburetor works. So the idea of this video is just to do that, just to kind of give you a basic understanding of what goes on inside a carburetor. Here we have a small selection of carburetors, just to give you an idea of the variety of carburetors that have been used on vehicles that have been sold in the US. Here we have a Holley 4-barrel carburetor that was a very popular OEM, original equipment manufacturer carburetor, as well as a very popular aftermarket performance carburetor. Here's a 2-barrel Mikuni carburetor used on millions and millions of vehicles that have come from Japan. Rochester Quadrajet, used on many General Motors vehicles in the 60s, 70s, and into the 80s. Carter Thermal Quad, used on a lot of Chrysler products. This is a Carter AFB, kind of the predecessor of the Edelbrock Performer carburetor. That's a really popular aftermarket carburetor today. Here's a Solex, used on millions of air-cooled Volkswagens sold in this country. So as you can see, the variety of carburetors is tremendous, used on European cars, Asian imports, American domestic vehicles. And if you do have a car that uses a carburetor, you should know just a little bit about it. And again, that's the whole purpose of this video. If you read anything about carburetors, you'll always see a reference to Venturi effect. Venturi effect is the basic principle of a carburetor, how many of the circuits work on a carburetor. So what a Venturi is a restriction. This is the restriction. If you have air flowing into the carburetor, the air then hits the Venturi, or the restriction. The airspeed has to increase at that point. When the airspeed increases, the pressure drops. If you have some type of a passageway that leads, say, to a fuel reservoir, in that Venturi, as the pressure drops, fuel will then be drawn into that Venturi and then drawn into the engine. So a Venturi effect, again, is the basic principle of a carburetor. As we'll see, there are many circuits in a carburetor, or passageways, that have to deliver the correct air-fuel mixture depending on the load on the engine, the temperature of the engine, that kind of thing. Not all of them use Venturi effect, but the main amount of fuel that's delivered into the engine depends on Venturi effect. The air will enter the carburetor through the air horn. Typically, it would pass an air cleaner first. Then the air will pass through the Venturi. The velocity of the air increases, pressure drops. There'll be some type of a nozzle or a tube that comes from a float bowl, which is the fuel reservoir. Low pressure in the Venturi then draws fuel from the bowl into the Venturi, and then down past the throttle and into the engine. The carburetor is located on an intake manifold, which basically is the air and fuel passage that allows the air-fuel mixture to be drawn into the engine. Most vehicles that are on the road today that have carburetors use what are called downdraft carburetors. That means the air comes in through the top, pulled down through it into the engine. But there are a lot of variations of carburetor. You also have some vehicles that have been made with side draft carburetors, where the air would come in through the side, then drawn into the engine. They've even had updraft carburetors where the fuel will come from underneath and then drawn in through the carburetor. There are many, many different combinations. But the downdraft carburetor, as shown in this example, is the most common. It's the job of the carburetor to deliver a combustible mixture of air and fuel into the engine. A gasoline engine, ideally runs on what's called a stoichiometric mixture of a 14.7 to 1 air-fuel ratio. That means 14 parts of air to 1 part of fuel by weight. To do that, a carburetor has multiple circuits or passageways that will deliver the air-fuel mixture in that correct ratio depending on the needs of the engine. The needs of the engine for idle is different than wide open throttle. Pressing the accelerator pedal might have a different demand than cruising along at a steady speed. Starting the vehicle has a different demand also. So you have various circuits or passageways that supply that stoichiometric mixture to the engine depending on the needs. So what this is a list of 7 basic circuits, which are about the most common that you'll have in a carburetor. You may have some carburetors that might have an extra circuit or two. Some might have less. You know, carburetors have been used on a lot of things, not just cars. So you might find something that would be on a lawnmower will have different requirements than something's on a car or a chainsaw. So it really just depends. But the circuits we're going to look at, which are the most common, you have what's called a float circuit, an idle circuit, off idle circuit, main metering circuit, full power circuit, accelerator pump circuit, and a choke circuit. These 7 circuits should be able to deliver the correct mixture to the engine to meet the demands of the driver, whether it be idling, cruising, accelerating, starting, whatever. And we're going to take a look at all 7 of those circuits. All carburetors have some type of a reservoir where fuel is held and then allowed to be delivered from that reservoir to the various circuits in the carburetor. So typically, fuel would be drawn from the fuel tank by a mechanical engine-driven pump, and then that fuel under pressure is then pushed up into this float bowl. Typically, carburetors, they use relatively low pressure compared to fuel-injected cars, so the fuel from the mechanical pump would be typically somewhere in the 4 to 7 or 8 psi range. What's going to control the level of fuel in the bowl is a needle and seat and also a float. And we'll take a look now at how that works. The float system in a carburetor works basically like the float in a toilet tank. As you use fuel out of the bowl, the level of fuel drops. The fuel pump then pumps fuel into that reservoir. There's a float that's sitting on the level of fuel. It drops. When it drops, it opens up a needle, which is allowing the fuel to pass into the reservoir. As the fuel demand decreases, the float level, level of fuel in the float bowl increases. That raises the float. That pushes a needle into the seat, and then that shuts off the fuel supply. The pump continues to pump, but it won't pump more than what the pump is designed and regulated to internally. And then this needle, when closed, will not allow more fuel to pass until the fuel demands increase, the float again drops, the needle drops, and then fuel from the pump is able to flow back into the bowl. So it's a continuous process, and that is your basic float operation. All carburetors have to have some type of an idle circuit. At idle, the fuel requirements are very low. So we have a system then that starts with the float bowl, and then fuel will be delivered past an idle mixture needle and underneath the throttle plate. The reason is, at this point, we don't have enough air volume through the venturi. We're not going to be able to pull fuel into the venturi. We're going to be depending on engine vacuum to create a low pressure area that will allow that fuel to be drawn out of the float bowl. So what we have here is fuel in the bowl. It'll come through a passage, past what they might call an idle jet, a low speed jet. Sometimes they'll call it a pilot jet. It'll then actually mix with air with what they call an air bleed, right in this area. And so air then is going to be able to be added to the fuel, which will help to emulsify it, which will make it a lot easier to turn it into basically an atomized and ultimately a vaporized mixture. So that fuel then is drawn down this passage, past the idle mixture screw. The idle mixture screw then is the adjustment that is made to carburetors. Typically when you say the carburetor needs adjusting, when this mixture screw is adjusted, it increases or decreases the amount of volume of fuel that can pass in this area. And really the idle mixture screw is only used for an idle adjustment. It doesn't do anything for the other modes and the other circuits in the carburetor. So when you adjust a carburetor, you're actually adjusting the idle circuit. So then that fuel is then drawn by vacuum or the low pressure that's created by the cylinders underneath the throttle plate. So very little air is passing the throttle plate right now. You don't have a great demand on the engine. There's very little load. You just need enough fuel to keep the engine running. That basically is our idle circuit. When you want to get the car to start moving, you need more fuel. You need more fuel than the idle circuit is able to deliver. So for that, we have our off-idle circuit or off-idle system. So as we start to open up the throttle plate, we're going to allow more air. At the same time, we have to admit more fuel. So you have passages actually that are above the throttle plate that are not controlled by the mixture screw that will start to deliver fuel to match the amount of air that is entering. So here they're showing like two passageways that are above the the idle passageway underneath the throttle. So as we open the throttle more, now we get even more fuel that's coming out of those passageways. And so again, that is going to increase the fuel volume to match the amount of air that we're adding, with the whole idea of trying to keep that approximately 14.7 to 1 air-fuel ratio correct. Carburetors do a fairly good job at that, but nowhere near as well as the fuel injection systems that we have today, which are much more accurate and much more precise. But I say they did pretty well for their day. When the car gets up to 25, 30 miles an hour, you're going to need more fuel. So you're at the point where you have a much greater load demand on the engine. The throttle is much more open. Here they're showing it wide open throttle. We don't have to be wide open throttle. We just have to be at a point where we're beyond what the off-idle circuit can deliver. So now we're going to have enough of, through Venturi effect, enough of a low pressure area in the Venturi of the carburetor that we're going to start drawing fuel through what they call a main jet. That main jet then is going to allow fuel to be drawn up to a discharge nozzle that's just above the Venturi. Then that low pressure that's being created right in this area is going to draw fuel to match the amount of air that is being pulled into the engine, and then we'll be able to deliver the correct air-fuel ratio for that demand. The main metering circuit probably delivers the majority of the fuel during the operation of the engine. Main metering could work somewhere between about, let's say, 25 and 60 or 70 miles an hour. There are times we need more fuel than the main metering circuit can deliver. And so for that, we have the full power circuit. Let's say if we're cruising along at 60 or 60, 70 miles an hour, and we suddenly want to accelerate. That means we're going to pop the throttle open even further, and that means more air, we need more fuel. The main metering circuit actually is designed to deliver the power you need and for the speed that you want, but economy is still a factor. So you need something that's going to put more fuel into the main metering circuit when you have that extra demand. So you're on the freeway and you want to pass a car. For that, then, you're going to need more fuel into that circuit. That's where the power system comes in. In this case, there are a few different types. This one would use what they call metering rods. So you have a metering rod that normally sits down in the jet. It's blocking the jet. It's basically taking up space, limiting the amount of fuel that can go through that jet. If you suddenly trump on the throttle, you might either mechanically or by vacuum in a spring pull that metering rod out of the jet. That's going to allow more fuel past the jet, then be drawn up the passage, and then discharged into the venturi. That is your full power system. But that one, again, would use metering rods. Let's look at a different type. This carburetor would use a power circuit that doesn't use metering rods. This would use a power valve, like Holley carburetors for years have used power valves. Others have also. So we have our main jet here that normally would be delivering fuel to the main circuit through the passageway and then into the venturi. But under certain load conditions, and we'll take a better look at this in the next slide, we have vacuum and a spring controlling a valve. When this valve is closed, only fuel is allowed to go through the main jet. When that valve opens, because of engine load, it allows extra fuel to go into the main metering circuit, basically around the main jet, and then that will basically enrich the mixture for that temporary burst of speed that we need, say, when we are passing a car. And that is your another type of power circuit. For a better look at the power valve, when we have high vacuum in the intake manifold, that indicates a low power demand. So that strong vacuum is actually pulling down on the power valve against spring tension here. That's closing up this passageway that's right in this area. It's a little hard to see in this illustration. So the only fuel that you can get now is through the main jet and then discharged into the venturi. Suddenly you trump on the throttle, you have a high power demand, low vacuum in the intake manifold. The vacuum is so low, the spring tension on the power valve is great enough that it will pull the power valve up, and then you have, again, a little hard to see, small passageway here that would allow more fuel from the float bowl to enter the fuel that's already coming through the main jet and then up through the passageway and discharged into the venturi. So again, that's the action of a vacuum controlled power circuit. Air will move a lot faster than fuel. So anytime you move the throttle, you're going to allow a lot more air into that engine, and the fuel will lag behind. That's not good. If that happens, you will get what they call a hesitation or a sag that is definitely very undesirable. So what you have to combat that is an accelerator pump system or an acceleration system. And there are a few different types, but basically the function is the same. We're going to have a way of mechanically pumping fuel into the airflow. We're not going to depend on vacuum. We're not going to depend on venturi effect. We're going to actually mechanically pump it. So for here, we have an actual accelerator pump. This is a mechanical pump. There's a small pump reservoir that's attached to the float bowl, and it's mechanically operated by the throttle itself. If you've ever, let's say, are maybe in the position when you're trying to start a car, and one of the things you're going to check for if the car doesn't run is it's getting fuel, and you take off the air cleaner and you look down the air horn, you'll have somebody work the throttle, or maybe you do it yourself, and you'll see fuel squirting into the venturi if there's fuel in the carburetor. And that fuel is coming from the accelerator pump. And so the way it basically works, your throttle linkage then controls this pump. When your foot's off the accelerator, the pump is pulled up. That'll draw fuel from the float bowl past a check ball, fills the reservoir of the accelerator pump. Now when you push down on the throttle, it pushes down the pump. Because of this check ball, it prevents fuel from going back into the reservoir, but now you're going to push that fuel through a passageway, past some type of an outlet check ball or weight, and then it will squirt right out into the venturi. And again, the whole purpose of that is so it will be able to match the amount of air that is suddenly flowing into the engine because of the sudden throttle demand. And that's your accelerator pump system. Here's another type of accelerator pump. The one that we just looked at used a piston type pump. This is a diaphragm type pump, very commonly used in Holley carburetors and many, many others. So what we have here, instead of a piston, we actually have a rubber diaphragm and a spring, and so that reservoir, again, is connected to the float bowl, and we still have a mechanical lever that's attached to the throttle that when we push on the throttle, it actually moves the lever, pushes the diaphragm, and then allows fuel again to go up through the passage, past some type of an outlet check ball, and then would be squirted into the venturi. So it's just the different mechanics of doing the same job, whether it be a piston type pump or a diaphragm type pump. When engines are cold, they have a greater fuel demand. You need more fuel for a cold engine than you do a warm engine or one that's up at operating temperature. So you have to have some way of at least temporarily really enriching the mixture to get enough fuel into that engine so it'll start, and also so it will run decently while it's cold. So for that we have a choke. And our choke is a separate choke plate that's up at the top of the carburetor in the air horn that many people feel it's designed to cut out the air. Well, actually, it's not cutting out air. What it's doing is when that choke plate is closed or nearly closed, it doesn't close all the way, it's nearly closed, it's actually forming now a low pressure area right in the venturi. Because now, because we have basically, we've blocked off the passageway here, we've now, rather than just having the low pressure area here underneath the throttle plate, which they're not showing here, we're going to create the low pressure area right at the venturi, even though we have a very low amount of air volume. So in this case then, rather than just delivering fuel through the idle circuit while we crank the engine over and while the engine's running cold, we're going to be able to pull fuel through the main metering jet up through that passageway and allow it to discharge through main metering, even though we don't have that kind of load where we need that much fuel for main metering. We now have that kind of situation where we need that fuel, but because the engine is cold. So again, that's the whole purpose of the choke. At one time, chokes were manually operated. You'd actually have a lever or cable you'd pull, and that would close the choke. You'd start the car, you'd run it for a while with the choke on, then you'd have to remember to push the choke in. That was done long time ago. For many years, though, the automatic choke has been around. And so for that, you'll have some type of a system. This one would use what they call a bimetallic spring, which is a wound spring made of two different metals that react to heat. And so as this spring is cold, when you start the car, it tightens up, and there's manual linkage that makes the choke close. As the choke spring warms up, and there are different ways of warming up that choke spring. It might be an electric choke. They might run hot air from what they call a heat stove up into an area around the spring, whatever. But then as that spring begins to relax, it then takes the tension off the linkage and the plate starts to open. And that basically is your choke system. So we just looked at the 7 basic circuits that are in a carburetor. Our float circuit, our idle circuit, off idle, main metering circuit, full power, accelerator pump circuit, and choke circuit. So with those basic circuits, we're able to supply the correct air-fuel ratio depending on what the performance demand is on the engine. Again, there are lots of different types of carburetors, lots of different designs, but these circuits are a commonality between all of them. They might do things in slightly different ways, but they're still using these basic circuits. I'd say if you want to learn more about carburetors, if you have a chance, if you're at a swap meet or garage sale or something and you see one that's cheap, buy it and take it home and put it on your workbench and take it apart and look at the pieces. Try to identify those components. Find the main jet and say the discharge nodules for the accelerator pump, and look at the floats and the float circuit, the choke, all those different components. And you can try to start tracing down some of those passageways. Again, it's really not that complicated. So I hope you learned a little bit about carburetors. Thanks for watching.